Okay, this is a question that comes straight out of our textbook. Simply asks you, which compound is aromatic? So put another way is this compound, is this aromatic or not? So this is called naphthalene. So naphthalene, which is basically what mothballs are. I don't know how popular mothballs are these days. If anybody has some expensive cashmere sweaters or something, you may be protecting them with mothballs, or if you're into tying, flies for fly fishing, you might need mothballs to protect, your feathers or whatever it is you're keeping in your house. But what about the molecule naphthalene? Hey, could anybody surmise as to whether this molecule is aromatic or not, based off of the Huckel rule and the rules for aromaticity? Would naphthalene be an aromatic compound? Yeah, it's an aromatic compound. Remember, when something is aromatic, okay, aromatic, it's got to have a continuously overlapping system of p orbitals. Okay, so that's the first criterion. And then it has to have 4n plus 2 pi electrons. Okay, well, 4n plus 2 electrons in that continuously overlapping system of p orbitals, where n is an integer. N is 0, 1, 2, 3, etc., etc. So the reason my student said that this molecule is aromatic is because every single carbon in naphthalene, they're all sp2 hybridized. That means that every single one of them has an unhybridized p orbital on it, right? Now, if I look at the total number of pi electrons, there's no lone pairs to consider here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is 10 a Huckel number? Well, remember, it's an odd number of pairs, right? 10 is the total number of electrons. 10 divided by 2 is 5. 5 is an odd number. So that's an odd number of electron pairs. If you're like, I can't figure that out, if you need to look at the formula, right? 4n plus 2, when n is equal to 2, then I would have a total of 4 times 2, which is 8, plus 2, which is 10. 10 pi electrons. And I have, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is an aromatic compound. So we'll put here aromatic. Aromatic. Okay? This compound here is called 10-annuline. It's a compound that I brought up earlier on in the lecture, last class. Is 10-annuline, would this be an aromatic compound? Right, it is a non-aromatic compound. Why is it non-aromatic? Well, we went over this last class, okay? If you go into aromatic compounds other than benzene, we talked about the annulines and we explained why this compound is non-aromatic, okay? Non-aromatic. If you look at it, just quickly, you might think, well, it's got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi electrons, right? We have every carbon is sp2 hybridized, so we have the p orbitals, the closed ring. Everything looks good, but there's a problem, isn't there? Right? I have a hydrogen coming in here like this, and I have another hydrogen going in here like this. You see how it's very hard for me to write those two hydrogens in there. So there's a steric interaction, which causes this 10-membered ring to go out of planarity. And so the reason why is we'll put non-aromatic, since it is not planar, right? That continuously overlapping system of p orbitals has to be planar. Okay, if I move on to the next compound, C, would this be an aromatic compound or a non-aromatic compound? What about C? This one's a little more challenging, isn't it, right? Because you only have one pi bond in the whole molecule, but it's non-aromatic. Okay, if you think about it, it's a non-aromatic compound. Remember that the lone pairs on the oxygens, right? Those are kind of up for grabs. Are they going to be in unhybridized p orbitals, or is this oxygen sp3 hybridized, right? The question is this sp2 or sp3, right? If it's sp3, then both of the lone pairs are sp3. If it's sp2, then one of the lone pairs is in a p orbital, right? To make that continuously overlapping system of p orbitals. Well, if you think about it, we get a problem here, right? Houston, we have a problem. If we were to try to put a lone pair here in a p orbital, let's say we did have one, because we've got one here, we've got one here. Well, if that was in an unhybridized p orbital, then you'd have a total of 1, 2, 3, 4 pi electrons, and 4 is not a Huckel number, is it? Right? That's 4n, where n is equal to 1. So then we have a problem. So you're like, well, if I want a Huckel number, I'll need 6. So I'll take 2 more, right? So I'll put an unhybridized p orbital on this, and then I have a total of 1, 2, 3, 4, 5, 6 p orbitals. Well, you've still got a problem, right? Because you've got a Huckel number, technically, or theoretically is what I should say. You've got theoretically a Huckel number, right? Again, I'll use the green pen. You've got 1, 2, 3, 4, 5, 6 pi electrons. 6 is a Huckel number, okay? It's an odd number of electron pairs. 1, 2, 3. 3 is an odd number, but there's a problem because you have this oxygen here. If this oxygen was sp2 hybridized, then you'd have this pair of electrons in an unhybridized p orbital. Then you'd have 4n pi electrons. Then it's anti-aromatic. But remember, a compound will do whatever it can to avoid becoming anti-aromatic. And so one of the oxygens, and you could put an arrow to any one of the three, it doesn't matter, but this one here is going to be sp3 hybridized in order to avoid being anti-aromatic. And so the answer is this compound is non-aromatic, right? Because this oxygen adopts an sp3 hybridization so that it does not become anti-aromatic. So this is non-aromatic. Aromatic. Here we go. And let's try D. What about D? Would D be an aromatic compound? While you're thinking about that, I'll move on to writing out the next one. Would D be aromatic? You can see how these would lend themselves to multiple choice questions really easily. All I have to do is write down the structure of a molecule and say, is it aromatic or not? You know, or I could put down 3 and say, which ones are aromatic? 1, 2, 1 and 2, 1 and 3, 2 and 3, right? So you've got to be able to answer this. Is this compound aromatic? The answer is yes. Yes, it is. Remember that when you have a lone pair on an atom, okay, like this nitrogen, that's got a double bond and a lone pair, both of them cannot be participating in resonance. It's impossible. And so if we take this pi bond as 1, 2, 3, 4, and if we take one of the pairs of electrons, if we say that this oxygen is sp2 hybridized and we put this pair of electrons in an unhybridized p orbital, then we have, look, we have a p orbital here for the pi bond, we have a p orbital here for the pi bond, we've got a p orbital there with a pair of electrons, one here, one here. Now we've got a continuously overlapping system of p orbitals, and we have a total of what? We've got 1, 2, 3, 4, 5, 6 pi electrons. And so if you look at the Huckel number, 4n plus 2, when n is equal to 1, you have 6 pi electrons, right? An odd number of electron pairs. 1, 2, 3. 3 is an odd number. So there you go. This is an aromatic compound. So this is aromatic. Okay, and this is called oxazole. Anyhow, that's neither here nor there, but it's just kind of fun. Okay, could anybody answer E? I have this cation here. Would this be aromatic or non-aromatic or anti-aromatic? Does anybody have a thought about this one? This one I'd say it should be pretty abundantly clear. And again, nothing's easy in organic chemistry, but I'd say this one's a little more abundantly clear than some of the other ones. Would this be an aromatic compound? No, right? It's impossible. Why? Because you've got a big old sp3 hybridized carbon in there, right? This carbon has 2 hydrogens attached to it, right? Therefore, it's sp3. So you don't have a continuously overlapping system of p orbitals. Therefore, this is non-aromatic. You do not have that, again, continuously overlapping system of p orbitals. Okay, let's move on to question 17.34. We won't do the whole thing. We'll do a couple of them. All right, so this is 17.34. All right, 17.34. It just says identify the compound as being aromatic, non-aromatic, or anti-aromatic. Which one is it? All right, so we'll start with A, which is a 7-membered ring, which I hate drawing, but whatever. Give it the old college try here. There we go. That's not too bad. So while you're thinking about A, good gravy. B is also a 7-membered ring. There we go. Like that. I'll even draw a C in here. There's C. Okay. So what do you think about A? Would A be aromatic, non-aromatic, or anti-aromatic? Keep in mind that a molecule will do whatever it can to avoid becoming anti-aromatic, and a molecule will do whatever it can, if it can, to become aromatic, right? Yeah, it's going to be a non-aromatic compound. Why? Because we have 1, 2, 3 pairs of pi electrons here in the pi bonds, for sure. We can't change that. Now, if we were to render the oxygen sp2 hybridized so that one of the lone pairs is in an unhybridized p orbital, then you'd have a non-Huckel number, wouldn't you? You'd have an even number of electron pairs. You'd have 4n, where n is equal to 2, because you'd have 8 pi electrons. Then it would be anti-aromatic. But remember, the molecule will do whatever it can, whatever is in its power to become, or to avoid becoming, anti-aromatic. And so this oxygen is going to become sp3 hybridized, right? Both of these lone pairs will go into sp3 hybrid orbitals so that this can be non-aromatic. All right. What about B? What about Bob? I mean, what about B? I don't know if anybody's ever seen that movie. What about Bob? Does anybody have any thoughts about B? I see somebody says it's non-aromatic. Does anybody else have an idea about B? Would this be an aromatic compound, anti-aromatic, non-aromatic? We take the same approach that we did for A. Look, the pi bonds are always going to be pi, right? You can't take the pi electrons and change them into something else. It's only the lone pair that there's some ambiguity. You need to figure that out. So look, we've got 1, 2, 3, 4, 5, 6. If the nitrogen was sp2, okay, that means the lone pair would be in a p orbital. Then you'd have a total of 1, 2, 3, 4, 5, 6, 7, 8, which is a 4n number where n is equal to 2. Then you'd have 8 pi electrons, which means it would be anti-aromatic. But remember, this nitrogen is going to do whatever the heck it's got to do to avoid being anti-aromatic. So what kind of hybridization do you think it's going to adopt? It's going to become what? sp. It's going to become sp3, right? If it's sp3, okay, then we break up the continuously overlapping system of p orbitals, and we have a molecule that is non-aromatic. So we have a non-aromatic compound. Let's move down to C. C is called thiazole. Remember that this nitrogen, we have a pi bond and a lone pair on the same atom. The two of them cannot be participating in resonance simultaneously. It's going to be the pi bond, okay, and this pi bond. So I've got 1, 2, 3, 4. That's a non-Huckel number. But if I took one of the lone pairs on here, right, if this sulfur was sp2 hybridized and this lone pair was in an unhybridized p orbital, then I'd have 6 pi electrons, which is an odd number of pairs of electrons. And I have a continuously overlapping system of p orbitals, and therefore this would be an aromatic compound, right? So this would be, oops, this would be aromatic. Let's try one more. Okay, let's try D. So I've got a 6-membered ring, and it kind of looks like pyridine, doesn't it? Except it's got another nitrogen in it. This is called pyrazine. Pyrazine. Okay. Well, look, I've got 1, 2, 3 pi bonds. That's a Huckel number, just like benzene, right? You've got 3 pi bonds in a continuously, in a cyclic molecule. So really, it all boils down to what's the hybridization of the 2 nitrogens. Well, if the 2 nitrogens, if this one and this one, if they are both sp2, right, and these lone pairs are in oops, I missed the other lone pair. If this lone pair and this lone pair, if they're both in sp2 hybridized orbitals, I've still got the p orbitals because they both have a pi bond attached to them. And so I would have a continuously overlapping system of p orbitals, and I have a Huckel number of pi electrons. And so this would be an aromatic compound.